So I thought I'd spend a little bit of time going over the test objectives and also the formulas. I've got the formula sheet shown right here. It looks like you might be saying that that's not really that many formulas. We use a lot more formulas than that. And maybe you did, but really the more formulas that you used were just derivatives of this. So for example, if you had a question where you were given velocity and you were given time, you could have, and you needed to find displacement, you could have used that average velocity formula. Oops, don't have my pen ready. So let's say you were given V and T, and you're asked to find delta X, you'd still use this formula. You'd say, okay, excuse me, if I need to find delta X, I'm going to multiply both sides by T. So V average times T equals delta X. And you can say, well, that's another formula. Why didn't you put that on there? But that's really just this formula with algebra and algebraic manipulation. So I'm not going to put all the possible algebraic manipulations on there. There are a couple other equations you might wonder why they aren't on there. One of them, this is a little bit generic, but I didn't put any of the Freefall equations on there because they're just iterations of this same thing. So for Freefall, y equals y0 plus v0 in the y direction, t, and then minus 1/2 g t squared. But this is really just, I didn't get a chance to select my colors here. This is really just that. Another equation that I didn't include, it's in the projectile motion part, is the range equation. The reason I didn't include that in my list of formulas to use is because that can be misleading. The range equation is applicable for just a very special circumstance, and some of the problems in the book, many of the problems in the book, don't fit that circumstance. Sorry, lost my ability to speak there. So the range equation is appropriate when the takeoff and the landing part are at the same location. So for example, so if I have a ball here and I toss the ball and then I catch it at the same level, I could use the range equation. But if I toss the ball and catch it up higher, I can't use the range equation for that one. It's not applicable for that situation. So each of the slides that I have here are covering the different objectives on the test objective sheet, which is on Canvas. But I thought I'd spend a little bit of time not starting with that, but going over, and not doing them completely, but going over a little bit a couple problems that students had trouble with on the practice homework assignment number 5. These were the two lowest average scored problems by far. And I know this is kind of fuzzy and printed a little bit tiny. I just quickly scanned this from the PDF version of the book. And you would have had the same problem written a little bit differently, but with different numbers. Most of the problems on the homework are taken from the OpenStax physics book. So an archer shoots an arrow at a 75-meter distant target. The bullseye is at the same height as the release height. At what angle must the arrow be released to hit the bullseye if its initial speed is 35 meters per second? So if you were to shoot the arrow straight, and let's just do a quick drawing over here with it straight. So if you were to shoot arrow straight, so if there's your arrow, this is your target, and you were to shoot it, you know that it would actually hit below the target. Anybody who hunts would know that. I'm not a hunter myself, and actually sights in guns and even big guns on ships, they account for that. They actually account for quite a few things. That's why people take readings of the environment, and it depends on where you are in the world as well, how much the bullet or the projectile deviates from going in just a rigid straight line. So you know you've got to shoot up in the air. And I've got my notes here. So it's going to look something like that. Shoot off at some angle, theta. So let's start with our knowns and unknowns. Doesn't really matter where in the world we do this, so the initial position is not important to be a specific number, so we'll just say that's 0. The initial position here is also 0. Doesn't matter the time of the day that we do it, so we'll just start our clock at 0. We don't know theta, and in fact, at what angle. That's what we want to know, so let's just circle that with a different color. We'll use this light blue here, or aqua, I don't know, I'm not very good at deciding what colors are. And then we also have V0 equals 35 meters per second. So now it hits the target. It says that they are at the same level. So if the initial level was at 0 meters, then the final level will be at 0 meters. It says it's 75 meters away. We don't know how long the arrow takes. We do know, since it's at the same level again, that the final velocity is also going to be, the magnitude of the final velocity is also going to be 35 meters per second. And whatever this angle is, theta here, the final velocity is going to be the same angle below the horizontal. So that, I think, is all we need. So the theme for a lot of these projectile motion problems, purple, so the theme seems to be to analyze the x and y components of motion separately. And then use info from 1 to plug into the other. So here we're trying to find theta. So we need an equation that has theta in it. So if we go back to our equations here, you'll see that these equations here are really generic. And by the way, for the test, if you want to print this out, I have this on Canvas. And if you want to annotate it a little bit, this is just the bare bones. You could do well on the test with just these formulas and whatever you can derive from them. If you want to annotate the formula sheet, you certainly may do that. So this equation right here, you might be saying, well, it doesn't have theta in it, but V0, this is in the x direction. And if we go back to our, actually we can just look at this right here. So this is just a generic vector A. This generic vector A could represent velocity. This velocity then has a x component and a y component. So the x component of the velocity would be velocity times the cosine of theta if theta is measured with respect to the positive x-axis. So this equation right here actually does have theta in it. So if we use the x equation, so x equals x0 plus v0 xt plus 1/2 ax t squared. All right, so we didn't actually cover that. But if we assume no air resistance, so we are going to get AX equals 0, and AY, there is no force in the up and down direction except the gravitational pull of the Earth. So for this one here, we get that's equal to 0. That's equal to 0. And x equals v0 cosine theta t, where we're just using this general aspect right there. So this is pretty good, except you might be saying, so we don't know theta and we don't know t. Well, theta is our target variable, so not knowing that is what we would expect, but we don't know t. However, we can use the y equation to, no, not to, let's go with and solve for t. And then we can combine the two equations. So y equals y0 plus v0 yt plus 1/2 ay t squared. So in this one, this is 0, this is 0, and ay equals negative g. So if we combine those together, and also v0y equals v0 sine of theta. So if we combine all those items together, or those ideas together, we get V0 sine theta t equals 1/2 g t squared. So what I did is I plugged in negative g, moved this to the other side of the equation. Since this is a minus and we moved it to the other side of the equation, it ends up as a positive like this. So I notice now that there's a t squared term on one side and a t term on the other. So I didn't put a blank slide right after this one. I should have done that. But this is our arrow problem continued. So first we had x equals V0 cosine theta t, and now we just found that V0 sine theta equals 1/2 gt. So we can solve this one for t. We get t equals x over V0 cosine theta. And then we can plug that in, and then we eliminate t. So V0 sine theta equals 1/2 g, and now instead of t, we're going to put x over V0 cosine theta. And then we can solve this one for theta. And the book has a little relationship here because we're going to end up with 2 sine theta cosine theta. That's going to equal sine of 2 theta. It's just one of those trig relationships that if you had asked me before I read the book, I'm sure I knew it at one time, but I forgot, and now the book reminded me again. So the theme here, we analyzed the two components separately. We used this equation and this equation, which is really the same equation, just with different subscripts. Solved one of them for a variable, not the target variable, and then plugged it into the other to isolate the target variable. So part B, forgot about part B. So for part B, at the halfway point, because it mentions there's a large tree halfway between the archer and an overhanging horizontal branch 3.5 meters above the release point of the arrow. Will the arrow go over or under the branch? So at the halfway point, the y component of the velocity is going to equal 0. So let me find my notes here. So if we use our favorite equation here, y equals y0 plus v0y t plus 1/2 ay t squared. There's what we want, but we don't know time. So we can use a different equation for time. So we can use, if we go back to our formula sheet here. So we want something where we know everything but the target variable. So we know the initial positions and times, we know the acceleration, we know the initial velocity now because we know what theta is. So we can use this equation right here because we know everything about that for the y direction. And everything about that for the x direction too, for that matter. So we know that Vy equals Vy0 plus Ay times t. So Vy0 is the V0 sine theta. So that's 0 at the top. Vy0 equals V0 sine theta. A equals negative g. So we can rewrite this as 0 equals V0 sine theta minus g times t. And if we solve for t, we get t equals 1.13 seconds. And now we can plug that into here. And we actually find that y is going to equal, if we use these numbers, 6.23 meters, so it does go over branch. So that covers, strictly speaking, if you notice at the top of the formula, or the top of the problem sheet, and I'll go back to that in just a little bit, but I'll let folks copy things down here if they need to. But at the top of the formula sheet, that actually had objective 9, which is use the kinematics equations and knowledge of the independence of x and y motion to solve for an unknown quantity for a projectile. So that's what we've just done right here. But in doing that, we also practiced using some of the earlier kinematics equations as well. So this, let's go with a different color here. So this problem covered test objective. So we used the definition of acceleration. So we used kinematics equations of constant acceleration in the x direction and in the y direction, so a free fall direction. And 9. Another problem that folks had was this soccer ball problem. So let me find my notes on that. So suppose a soccer player kicks a ball from a distance 30 meters towards the goal. Find the initial speed of the ball if it just passes over the goal 2.5 meters above the ground, given the initial direction to be 40 meters above the horizontal. So we're kicking the ball like this, although now we don't want it when it gets back down to the ground level again. So we can say ground level is 0. Doesn't matter the time of day, so that's also equal to 0. Theta equals 40 degrees. V0, we don't know that, and that's actually our target variable. So now y0, or y, I'm sorry, is not 0. It's actually this 2.5 meters, I'm sorry, 2.4 meters above the ground. 30 meters from the goal, so x equals 30 meters. Don't know time. And we don't know the final velocity either. So we want to know V0. So we can use, this is just like the problem we just did, x equals x0 plus V0 x t plus 1/2 ax t squared. So if we assume no air resistance, then ax equals 0. And this is only being influenced by the gravitational pull of the Earth, so ay equals -g. I'm going to take a quick check here. Did I put ay? Yeah, okay. I thought maybe I put a here. So yes, ay equals -g. So in this case, ax equals 0. So that equals 0. This equals 0. X equals V0 cosine theta times t. So we've got two things we don't know. We don't know theta. Oops, I'm sorry, we do know theta. Still thinking of the last problem. We don't know V0 and we don't know t. But the time that it takes to go this x displacement is also the time it takes to go the y displacement. So we can use the y equation as well. So y equals y0 plus V0, and I'm going to skip a couple steps here because we just did this one before. Sine theta t minus 1/2 g t squared. So here we've got the same two unknowns. We don't know theta, we don't know t. Y0 is equal to 0. So what we can do here is solve the x equation for t. Plug that into the y equation. Let's see, how much of this do I want to do? Yeah, I don't want to go over that much here. But you're going to have a V0 from this term, a V0 from here. you're going to have to do a bit of algebra. So, and actually on the test, I would never ask you to do this much algebra. You're going to get V0 equals 18.2 meters per second. So the important aspect of this isn't the algebra. The important aspect is, first off, that I very carefully, so note my careful diagram and listing of knowns and unknowns. And then also how I used the x and the y equations. So folks that are watching, any questions from you people? If you have a microphone, you can ask, or perhaps better, if it's complex, probably verbal is better, but otherwise you can just type into the chat box. Once again, we are using our kinematics equations here. So this type of problem helps us practice using the kinematics equations, and it helps us practice using them together for projectile motion. All right, so we've got two of the good students in the class said they have no questions. So we'll go back over the formulas here, and then I'm just going to go through the objectives here, either two at a time or one at a time. Just talk about them a little bit. You can see I don't have a lot on the sheet here because I hadn't completely thought about how to talk about them. First I thought I could go over a problem for each, but then that would have taken way too much time. And I looked and I saw that folks had trouble with the two that I had just gone over. So I thought the best use of time is always to go over those problems that students had some issues with. But really, so apply the definition of average velocity to solve for an unknown. So I sort of did that at, oops, I don't like that color, for mainline notes, because that's too difficult to see. So the generic equation is this one right here. The book likes to use those approximations. So x final minus x initial over t final minus t initial. So they just call x final x, and they call t final t, and they say the initial time is 0. So knowing what this is, and I'm going to relate this to graphs in just a little bit. So basically being able to apply this equation right here, you'll notice that we've essentially used this a lot of times. So this equation here, the x equals x0 equation, we could always use that for one-dimensional motion too, and it gives us the same information. Plus v0 x t plus 1/2 a x t squared. So if ax equals 0, the velocity is constant, which means that the initial velocity is the middle velocity, and it's the final velocity as well. And we'll just generically say that's v at any time. So applying that, so we already said this is 0. Oh, and if it's the velocity at any time, that's also going to equal the average velocity. If you have $5 in your wallet the whole day, the average amount of money you have in your wallet is $5. So if you've got a constant amount of money in your wallet, the amount you have at any given time is $5. The average amount is $5 as well. So that's really all this is saying right here. But we've got x equals x0 plus v bar times t. So we can do a little algebra. X minus x0 equals v bar times t divided by both sides by t. X minus x0 over t equals v bar. So that tells us that this long equation reduces to the definition of average velocity when a equals 0. And that's kind of neat to know. Same sort of thing for number 2. I guess I didn't use my space very wisely here. I was thinking, oh, I'd have all this space for this one here. Number 2, so let's go with black. So A equals delta V over delta T. The book likes to use this V minus V0 over T format. We can adjust this a little bit, multiply both sides by T. AT equals V minus V0. Add V0 to both sides. V equals V0 plus A times T. For constant acceleration, the average acceleration is going to equal the acceleration at any given point. So once again, we're getting a formula here that we've seen before. And we have seen it before because we have another check mark there. So item number 3, we pretty much practiced that. Use the kinematics equations with constant acceleration to solve problems for an unknown given the appropriate information. So what that really means, let's break down some Bruce language here. So solve whatever given appropriate information. What that really means is you need to be able to solve formulas for some parameter that isn't already alone on the equal sign. All right, that sentence seemed better crafted in my brain. It doesn't look very good on the piece of paper. But anyway, that means, so for example, v equals v0 squared plus 2a x minus x0. That means if I give you a problem, I say, for example, a car skids to a stop from 60, no, that's going to be too fast. So we'll say, what would be good? 26. 26 meters per second. So it skids to a stop from 26 meters per second. The skid marks are 40 meters long. What was the acceleration of the car? So if you were in the mindset, oh, I need to find an equation where acceleration is alone on the left-hand side, and I'm lost if I can't, you'd stay lost, because the only equation that in which acceleration is already by itself is this one. And we don't know the time. So let's just take a quick look here. So possible equations to use. Well, one is v equals v0 plus a times t. One is x equals x0 plus v0 xt plus 1/2 ax t squared. I'm actually going to get rid of the subscript there because that was pretty ugly subscript. And of course another one is v squared, which I kind of set us up with, v0 squared plus 2a x minus x0. So if we critique these, this one's difficult to use. We don't know t. This one's difficult to use for the same reason. This one is the best choice because we know velocity final, skids to a stop. We know velocity initial, 26 meters per second. We know x minus x0 is 40 meters. So we can then solve for acceleration. So that's the type of stuff you should be able to do. So I listed 3 and 4 as separate objectives, but they're really the same thing. And like I said before, I didn't list them as separate equations. I'll skip that. So these two equations are essentially the same thing, the y equation and the x equation. So here we've got apply the relationships between the slopes of the graphs we've sketched in class. So you've sketched some in your homework. I've sketched some in the online classes here. And then the definitions to solve for an unknown. So for example, one of the things that we noticed is that the slope of the position versus time graph is the velocity graph. And notice how similar that looks to slope equals rise over run. So the rise for the position versus time graph is position. And remember, I complained about this before. The book really should be using not displacement, but it should be using position. All right, and the slope of velocity that's one of the world's worst spellings here of graph. I wouldn't even know what that says. I can't identify it right now. So A equals delta V over delta T, again, rise over run. So you should be able to go from the position versus time graph to the velocity versus time graph. So you can find velocity from a position versus time graph. You can find acceleration from a velocity versus time graph. So you should be familiar with those sort of transitions. You should be able to go from one graph to another. So for example, if I just gave you one of these, you should be able to describe the thing that made this motion. So you should be able to recognize that this is speeding up motion here. And that speeding up motion with a graph that looks like this, a position versus time graph that looks like that, results in a velocity versus time graph that looks like this, which results in an acceleration versus time graph that looks like this. You should also be able to recognize other types of graphs as well. So if I gave you a graph to look like this, you should recognize that this represents slowing down. So this would look like that. And then it would result in an acceleration versus time graph that would look like this, which should be a flat line. And finally, the last thing, the most recent thing that we have practiced is adding and subtracting vectors. And you should be able to graphically do it and do it analytically. And they really support each other. I mean, analytical, that method, of course, is more precise, but it's also a place where you can tend to make sign errors and get answers that just don't make sense. You say that motion is east, or motion is to the west, but you say it's positive, then you actually have it going to the east. And if you just blindly look at that number, you'll say, oh, here's the answer. But if you draw it out, that's really helpful. So let's just quickly draw this one out. A person runs due north for 10 kilometers. And we're going to use our scale here. So at this time, let's see, we want 2 kilometers equals 1 centimeter. So 1 centimeter scale equals 2 kilometers real. So the first one is 10 kilometers, so that's going to be five. Oh, and I forget if I can, yeah, so there. I forget if I can angle it afterwards. I think I can. Oh, no, I can't. I forgot. So let's go back to this, and then just kind of estimate like that. So, oops, that's not very good. So that's not a fantastic due north line. And then 15 kilometers an angle 20 degrees south of east. So 15 kilometers, that's going to be 7.5 centimeters scale. And I'll just guess. Here. And then 20 kilometers, 45 degrees north of west. So 20 kilometers is 10 centimeters. There's about 45 degrees. So there we go. We're expecting our end result to be pretty close to due north. So what we've just done is that right there. So in order to do it analytically, we need to, so we know that Rx is going to look something like so Rx equals AX plus BX plus CX. So AX equals 0 plus, and now we need to go with our, let's use a different color. Oh wait, actually it said north of west. Of course, it doesn't really matter. North of west and west of north are the same, but I want to be correct. So there is, so that could be theta 1, that could be theta 2. Forgot the plus sign there. Okay, so BX 15, 30 degrees south of east. So when we do this, it's below. We could either take our angle all the way around and say that's 340 degrees, and then we'd end up with the right number. But I like to just look at the sketch, recognize that this is below the axis, put the negative right there, and then that's going to be, so x is the adjacent, so cosine, not 15. And now the next one is oops, sorry. So we're in the x direction. So this is, so yeah, that's actually why you draw it like this, because if I would have just been thinking through it, kept that negative there, it probably would have stayed there because I wouldn't really have had a method to check things out. But we're talking about x, so the x component of A, and let's label those. I should have done that as well. So that's A, that's B, and that's C. That'll really help. So 15 times cosine of 20. Now this one is going to be backwards. So this one's going to be minus 20 kilometers times the cosine of 45 degrees. So whatever that comes out to be, I just made up these numbers right before class. So Ry is going to equal AY plus by plus cy. So ay, there is no angle for this one. It's just straight up 10 kilometers. And for this one now, we've got the negative in there because it's downward. So minus 15 times the sine of 20. And now the y component of vector c is up. So plus 20 times the sine of 45 degrees kilometers. So then r is going to equal square root of rx squared plus ry squared. And we're going to end up with a little triangle. And I just made these numbers up, so it'd be quite coincidental if it did actually add up, so the resultant was right on the y-axis. And then what I would do is actually sketch the resultant. So however that's going to look, maybe it's this plus that, so ry. Let's make that a different color. Yeah, I would actually sketch it out and then use the arctangent. All right, so questions or comments from folks? That pretty much covers all of the test objectives. Okay, well, thanks for watching either live or watching it on recording. It's probably a super exciting part of your day, going away from the exciting YouTube videos of athletes, celebrities, and cute kittens. We don't have a cute kitten at our house, but we do have a cute dog. So somehow I should probably figure out how to get the cute dog into the video. Anyway, thanks for watching.